Okay, part two, the last part for diodes. And so we're going to look at a couple more non-ideal factors. Breakdown was a non-ideal factor, and we're going to look at things such as power dissipation and contact potential in terms of how that affects diode behavior. Regarding power dissipation, you can see some of the non-ideal factors here. All these diodes are power diodes in one way or another, and they're attached to a huge heat sink. This is a laser diode here, so look at the size of the heat sink just attached to the laser diode. This is a white light-emitting diode, and this thing here is not just a printed circuit board to make electrical contact, but it's also acting as a heat sink. And so for a lot of these high-power applications, you can start to see some non-ideal effects, and we'll talk about a couple of other of those as well. So let's start with the first non-ideal effect. So for the ideal diode, we assume that as soon as you went above 0 volts, you got an exponential increase in voltage. But this is for the ideal diode equation. It doesn't basically take into consideration contact potential, because remember, my contact potential for a lightly doped diode, I might have a really small contact potential, but for a heavily doped diode, I might have a very large contact potential. And so you're like, well, the barrier here is obviously different than the barrier here, right, in terms of the doping levels. Let me put the Fermi levels in there so you can see the doping levels too. So should this not show up in terms of the threshold for current? We haven't taken that into consideration. So how can we take into consideration contact potential, which for a heavily doped diode, it might cause this to shift out to higher voltages because you have a bigger barrier you need to erase by raising these bands up and lowering these bands down. And so if you remember, when we derived contact potential, we were able to basically derive the following equation here, right? Where the contact potential is thermal voltage times the natural log of the doping on the p-type side, and the doping on the p-type side and number of holes on the n-type side. And we also said it was equal to the same thing, thermal voltage, let me see if I can write this out here, over Q, KT over Q, natural log of NA ND over NI squared too, right? So that's another way we could represent contact potential. And when we wanted to do a proof on that as well, and so we did this proof, and I won't go through it here, where we used these same equations, we rearranged them, we started substituting in doping levels as a function of Fermi level positions and distances from the band edges. We substituted them in, and we ended up with the contact potential being the energy on the valence side minus the energy on the P, energy on the valence side for the P minus the energy for the valence side for the N. And so all we had shown with this, again, was saying the contact potential, QV naught, this equation here, QV naught. So here's QV naught. I have QV naught here, and I have QV naught here, is equal to energy of the valence on the P side, this energy level right here, minus energy on the valence on the N side right here. And yeah, that's my contact potential. So that was just a simple way to confirm our derivation of contact potential and check it against a band diagram. That's going to become important in a second here. And so again, how can we correct for this? And so we assume that the diode turned on instantly at 0 volts with exponential increase in current, because as you raise this up, you're tapping into an exponentially increasing number of electrons that you can diffuse over to the other side, and that was because of my exponential function, which is my Fermi distribution. And so we had looked at that a while back too. So that's why I see an exponential increase. And we also said you never get to the density of states functions. At this point, you're already ready to blow up the diode in a puff of smoke, and so you never see the current start to not increase exponentially because of the density of states portion of this. So again, we're going to account for this with contact potential. And you can kind of start to visualize this here. Here's a lightly doped diode. Here's heavily doped on one side, and this is heavily doped on both sides. And you can see as you increase doping levels, the Fermi levels get closer to the conduction and valence band edges. And as a result, when you line the Fermi levels up, the contact potential increases. So what we're going to see is that for a regular diode, you might get an exponential that turns on a little bit above 0 volts. You increase the doping levels, P plus or N plus, the contact potential shifts out, and if you make it heavily doped on both sides, we'll see the contact potential and the threshold to get current flow shifts out even further because I have a bigger barrier to overcome. None of these, of course, are like the ideal equation, which started right at 0. So let's do it here. This is a very simple way to derive this. And so here is our diode equation. Here's I naught. So it's I naught e to the qv over kt minus 1. And what I'm going to do here is I'm going to substitute in for p sub n only. So this is a p plus n diode. Let's assume that we have a p plus n diode. If it's p plus n, if it's p plus, I can get of n sub p because this is number of electrons on the p plus side, and there are very few because they're recombining with the whole. So I'll get rid of this term. I'm just left with this term with p sub n. And then I'm going to substitute in this equation we had at the beginning of the course, which tells us how to calculate the whole concentration on the n-type side. So you have density of states and Fermi distribution as related to the energy levels and distances of the Fermi level from the band edges. So we'll take that old equation, we'll put it in here in a second. And so here's my I naught for a p plus n diode, e to the qv over kt. And let's assume we're in forward bias, so I'll get rid of the minus 1 and I'll simplify it down like that. So what I'm going to do is if I put this exponential in here, I've got an exponential here, and I've got an exponential here. I can combine the terms in the two exponentials into one. Density of state stays out front. Okay? And so look what I have here now. Let's take a look just at this term here. So let's take a look just at this term, because this term we already are familiar with, right? We're already familiar with e to the qv over kt, but what does this new term here do for us? Well, let's take a look at that term. I'll bring it over here. Okay? So this term is E Fermi in the n minus E valence in the n. E Fermi in minus E valence in the n. So the energy of the Fermi level in the n minus the energy level of the valence level in the, E Fermi in the n minus the energy of the valence level in the n. So it's basically saying this distance here. Okay? Well, what we see is that E Fermi in the n is equal to E Fermi in the p. Well, that's obvious. Fermi level in the n for a diode with no bias is equal to Fermi level in the p, right? The Fermi levels line up. So I'm going to get rid of Fermi level in the n and substitute in Fermi level in the p. Then I'm going to substitute Fermi level in the p with valence level in the p, because look, this is p plus. So the Fermi level in the p is really close to the valence level in the p. So I'm going to say they're equivalent, and then I end up with this, which says E valence in the p minus E valence in the n. Well, this is the difference between valence in the p and valence in the n, and lo and behold, that's just my contact potential. On an energy band diagram, it's QV naught, right? And so all I have to do then is take QV naught, substitute it in for this. I do that, and I end up with a modified diode equation where I now have contact potential subtracted from the applied voltage. And so what this means is that for forward bias, you need to overcome the contact potential with enough voltage to basically start to see this exponentially increase in current. So this was for P plus N, and it applies to N plus P, but let's just look at some nice examples here for P plus and N plus. So for P plus and N plus, you have a couple examples of a germanium, silicon, gallium arsenide, and gallium phosphide diode, and you see the current versus voltage plot. This is not a log scale, okay? So you can see it takes off exponentially, and it's about right at about 0.7 volts here it takes off. Well, that makes sense, because if I had P plus and N plus then, right, my Fermi levels are almost to the band edges for both cases. My contact potential is therefore basically almost equal to the band gap energy, right? Here's my band gap energy, and because my Fermi levels have shifted because of the heavy doping that close to the band edges, my contact potential is just about equal to the band gap energy. I'm sorry, I drew that as a Q, band gap there. And so you can see that on these diode plots for real diodes, turn on is almost close to the band gap for germanium. Silicon, the band gap's 1.1 volts. You can see at about 1 volt it turns on. Gallium arsenide, the band gap's 1.4. This is turning on very close to that as well. And gallium arsenide phosphide, a little bit wider band gap, you can see the turn on getting close to that as well. And so this shows you, with real data, how that when you dope a diode heavily, the threshold to turn it on increases out to the contact potential. So that's important when you go into the lab and you're like, well, why does my ideal diode equation not work? That's because you got to substitute in the contact potential if you want to make it work as predicted. I want to go back and know one more thing. Could my voltage ever exceed the contact potential? You'll never have your applied voltage exceed the contact potential because if it did, basically, at that point, your barrier completely disappears and you get so much current that your diode will essentially blow up, or you'll see resistance get in the way of it. So you never really get to the point where your applied voltage here exceeds the contact potential because you just get so much current through it. Okay, so if you have a diode which has a contact potential of 0.7 volts, you're not going to apply 4 volts across that and get 4 volts across the junction itself. If you see 4 volts, then you have 4 volts that's dropping across the wires and the semiconductor material. It's not dropped across the junction because the junction has just disappeared. It passes so much current. Okay, so let's keep going forward. Let's look at another non-ideal factor for a diode. So in forward bias, we've assumed two things. We've assumed that all the recombination occurs beyond the junction. So remember, for this diagram, I have holes that diffuse over here, and as they go into the n-type material, they recombine, right? And then I have electrons that diffuse over here, and as they go into the p-type material, they recombine with distance, and there is no recombination in the depletion region because there's no carriers basically to recombine with. I know I'm injecting some holes, but it's not like the holes see as many as electrons as they would see over here in the n-type region, so they don't recombine. And remember, the reason why the hole current dropped off like this is basically the holes disappearing as they recombine with the excess electrons that were brought over. And again, this is P plus N, so I have more holes than I do electrons. That's why this curve is above this curve here. And so we assumed with this that all the recombination occurs beyond the junction. So a hole has to go over here before it recombines, and an electron has to go all the way over here before it recombines. And we assumed that there was no recombination in the depletion region, the depletion or transition region. Names are equivalent. And so there's no recombination here. However, there are two exceptions to this. When I am at low voltages, my depletion region width can be very wide. Remember, when you forward bias a diode, you decrease the depletion region width. But for low voltages, the depletion region width could be so wide that it gives a better chance for a hole as it tries to make it across here to see an electron coming this way, and then they recombine. The other thing that could happen is when I go to very large voltages, my depletion region width becomes small, so it's difficult for them to have enough path to see each other, but at some point I could be pouring over so many holes this way and so many electrons this way, the concentrations being so high that they start to see each other and they start to recombine. So both at low voltages and high voltage, I can start to see recombination in the depletion region. So how will this change our diode behavior? Well, let's think about it this way. If I diffuse over one hole, so one hole goes over this way, okay? That hole will recombine over here, and that requires one electron to come in to recombine with it, right? And so the point being that for one hole of Q equals 1, I need an electron to come in that recombines with it, because as the hole recombines, it kills an electron, so I have to bring another electron in to recombine with it. So my total Q for this diode is 2 for that one hole. Now consider an electron going this way, that's Q equals 1 moving across there, recombines with a hole, so I get Q equals 2 there. Okay? And so my net charge exchange for one hole and one electron moving across is a Q total of 4. Across the depletion region, I have to move them, and then I have to bring one in to recombine for a total charge of 4. Now, what happens if they recombine here? Well, if they recombine here in the center, then instead of basically causing recombination, the hole can make it here, so the hole would make it here, okay? the electron would make it here, and they would recombine here, and my total Q in that case is equal to 2, where before my Q was equal to 4. Okay? Again, when the hole made it to the other side, I had Q equals 1 make it across, and it recombines with an electron, which requires me to bring another electron in, so a Q total of 4 for both the electrons and the holes. But if the hole goes across here and the electron comes this way and they recombine here, then the process is dead and killed with a total Q of 2, not a Q of 4. And so as a result, my diode is half efficient at generating current. And so how you account for this is that you take the diode equation and you have QV over KT and you introduce this ideality factor N, which ranges between 1 and 2. And so if you're in a region of bias where there's no recombination in the depletion region, then N equals 1, and I just have QV over KT. However, if you're at really low voltages or very high voltages where recombination in the depletion region can occur, then N could get to as great as 2 because you're going from a Q of 4 to a Q of 2, right? And so then N makes this half as efficient. And so for a given voltage, you only get half as efficient at basically, in a given charge, you're only half as efficient at generating current. Because again, if it's Q I'm measuring and it's coulombs per second, then if I have less Q, then I have less current. And so that's how we introduce that into the diode. The other thing we have to look at is when we go to high voltages and a lot of current, at some point the resistance of the depletion region just disappears. So this thing disappears, I can get all the electrons this way, all the holes this way. And so if this disappears, then what's left? Well, what's left is the semiconductor materials themselves have some resistance, right? And so I'll get a voltage drop across those. So if I have an applied voltage and I've got current and voltage drop across these resistors, then that will decrease the voltage applied across the junction. And so I could take my existing diode equation and basically do a simple summing of voltage around this loop. My voltage here applied across the junction will be equal to my applied voltage minus the voltage drops due to the resistance in the N and P-type regions. And so when you go to very high voltages and lots of current, you can also see non-ideal diode behavior because these resistances start to kick in and cause your applied voltage to less efficiently couple to the junction. So, bringing it all together, here's a plot of current on a log scale versus forward bias voltage. Now this is on a log scale, and so my exponential diode equation will look linear, okay? So that's why we're plotting this on a log scale. So here we are at 0 volts, we're starting to turn it on, and for low voltages, like I said, we had this ideality factor where N equals 2, because recombination is occurring inside the depletion region, my diode is half as efficient, and so my diode curve looks like this. Then when I get to normal bias, my depletion region shrinks enough such that the recombination in the depletion region goes away. Then I get back to N equals 1. This is my normal exponential increase in current, and the slope here is twice as much as the slope here, which makes sense because I'm plotting this function on a log scale, right? And it's exponential. Then I go to high enough injection levels. Sure, my depletion width is narrow, but I'm injecting so many electron and holes that they can start to see each other's concentrations in the depletion region, and again my ideality factor drops to 2, and I become half as efficient. The slope halves in terms of current versus voltage. And then lastly, if I go to a high enough voltage, I will run into ohmic effects as well, where the series resistance kicks in and the resistance of the diode itself has disappeared. Be careful though, for many diodes, for any of these, at some point this could be a puff of smoke, or maybe it's out here. And the big thing that helps you prevent it becoming a puff of smoke is just to cool it. So if you have a diode and you have some circuits attached to it, leads attached to it, if you want to get way out here, you typically have to have a huge heat sink to extract heat from the diode to keep it from essentially blowing up. Now, I want you to be careful with that Q equals 2 versus Q equals 4. And so here's a simple way to explain that. I have a reverse bias diode, okay? And it's not forward bias, but the main point I want to impart on you is that if you consider, measuring current in a circuit, all you'll do is measure your current out here. So if I want to measure the current, I'll measure the current out here. So here's my little current meter. I'm measuring the current through the outside circuit. Okay? From the outside circuit perspective, 2Q for inside the circuit is 1Q outside. Well, why is that? Well, let's say here's one electron. So here's Q equals 1. So 1 electron, Q equals 1. That 1 electron moves around here, it comes around, and as it goes through my current meter, I measure I've got Q equals 1 that went through that circuit. And let's say I've got a hole here, that would be Q equals 2 moving this way, right? So I have 1 this way, 2 this way. So I've got a total Q of 2. Well, the thing is when that electron comes back around here and recombines with this hole, it kills the hole off. So even if I have charge going this way and I've got charge going this way, and you'd say that's 2Q, because they're oppositely charged, with respect to the outside circuit, you only get Q equals 1 because as that electron comes back around, it recombines and kills off that hole. So the point was, on that previous slide where we had Q equals 2 versus Q equals 4, that was for inside the diode, not for the external circuit where you only see half the total charge in that picture. So, last topic. So far we've assumed, my analogy that you're walking down Main Street on campus and you find a hunk of P-type material, you find a hunk of N-type material, and you put them together in a vice grip and you make a p-n junction. But we know that that's not how you make p-n junctions in real life. And when you look at how you make p-n junctions in real life, that's why you get P plus N for almost all the examples we have in this class. And so why do we end up with P plus N in real life? Well, when we typically make a diode, we'll take a raw silicon that's been refined, we'll dope it N-type with phosphorus, and we'll create a long rod of N-type silicon. We'll then cut that up into a bunch of wafers, as you can see here, and then we'll put that N-type silicon wafers into a furnace with boron, which is a P-type dopant. If this is a high enough temperature, the boron diffuses into the wafer. So this is the wafer, it's N-type, and the boron will diffuse into the surface of the silicon, creating a P plus layer at the surface. And the reason why we do P plus is that if we want this to be P-type, we have to put a lot more boron than I originally had phosphorus. So I originally had N-type level of phosphorus. Well, if I want to make it P-type, then I need to have even more boron, which makes it P plus. And so now you can see why I get P plus N. What are the implications of this? Well, if you look at your concentration profiles, this is concentration versus distance from the surface, okay, for the boron and the phosphorus. Now remember, the phosphorus was what I mixed in with the silicon when I made that big rod. So it's evenly distributed in concentration throughout the whole wafer. The boron you're diffusing in, and you get a higher concentration right here at the interface. And as you go deeper in, it doesn't diffuse in as far, and it drops off versus distance. And so what you see is your junction will be where the P-type doping drops below the N-type doping, and you start to switch over to N-type. This side's P-type, this type's N-type. Which dopant dominates? And so my doping profile is no longer abrupt. Before I had P+, and then it just abruptly went into N-type material. Now I've got this sort of semi-linear doping profile, which I can plot as follows. This is Nd minus Na, and I get this linear approximation right here at the junction. And so how this changes my diode is, before, if I looked at my plot of charge, it was rectangles, right? Well, now it's going to be triangles, okay? Before I looked at my E field for the diode, I assumed it was triangular, right? Now it's got this, this curve shape, and I can use both of these to give you the contact potential. Does this change what we learned? Not substantially. It basically has a fine effect on the diode, but it's still exponential. It's still, most of the theory applies. But I want to show you for a real diode and how you make it. This is what the profiles for doping, charge, and E field will look like. Okay, so that completes it for diode. Make sure you can answer these questions. And for fun, check out this link. You can see that if you use diodes and you set them appropriately, you can actually make them swim on top of water. So check out this link as well, and you'll see a video of that happening. And I'll see you in class.